Great. Thank you for inviting me. As is probably cliche at this point, and every speaker will say, it's nice to be somewhere in person. It's been a while since I've been to Princeton, not least because of, well, mostly because of COVID, and I'm happy to be here. So thank you again for inviting me. To start the talk, and I can write on the left side of this. This is yes. Okay. Okay.
Sure. Maybe air a little to the right.
Okay. Okay. We'll do that. So. So I wanted to just start with the goal of the talk, which is that for a certain class of Legendrian surfaces, what I want to do is verify a conjecture, which is known as the representations are sheaves conjecture, which states that the moduli space, was there a comment? No, I'm just hearing things. Okay, good. Good to start off that way. Which is that some moduli space of representations of its Legendrian contact dg-A correspond to some extent expected moduli space of constructible sheaves. So there's a lot of things that are on this board that I have to tell you about. I have to tell you what Legendrian surfaces I'm interested in. Should probably remind you about what the Legendrian contact dg-algebra is and what the actual sheaves are. But you can think that really what this is getting at is, there's some conjecture that representations are sheaves. And in some cases, we have computations of this and verifications of this. But it's nice to have more verifications, and especially, the more verifications that you have, the more that you can kind of see some of the structure about what representations are sheaves is trying to say. So a lot of what I say will be combinatorial in nature, and the hope is that some of these combinatorics down the way sort of elucidate why one might expect representations to be sheaves. Okay, so the first thing I have to say is which Legendrians am I interested in? So let me just start a dimension down. I'm interested in Legendrian surfaces, but let me start with kind of an analogous setting of Legendrian knots. So suppose I draw a circle. Let me actually think about it this way. So suppose I draw a circle, and I'm going to imagine here that I've drawn this circle such that the left and right sides are identified. So here I'm thinking of my S1, and I've drawn these walls just to sort of indicate that I'm kind of thinking of the left and right-hand sides as glued together. And inside that circle, let me just specify some number of points. Let me say I draw, for simplicity, I'll draw, say, 3 points. So that's some combinatorial information that I'm starting with, some circle with these 3 points that I've chosen. And what I can do is in S1 cross R, so now these walls maybe make more sense in S1 cross R, what I can do is I can take a double cover of the circle, where what I have is that I have this immersed double cover where there's crossings at these 3 red points. So I have these 3 red points here. And I'm imagining, let me do blue. I'm imagining I'm taking some kind of immersion, which is doubled over the circle, and which is just, so it's immersed inside of S1 cross R. And I think about this as the front projection for a Legendrian knot. So I think about this as living inside of I think about this as the front projection for some Legendrian knot, which is living inside of the first jet space of S1, which is just S1 cross R or cross R2. And so you can imagine what I'm doing is I'm kind of thickening up these walls. I still have that my surface is kind of right here, but everywhere I saw a crossing, there's sort of an overcrossing and an undercrossing. Let me see that. Okay. If I think of this coordinate as Q, this Q coordinate say as Z, and let me call the third coordinate P, then what I'm doing is I'm building a Legendrian with respect to the contact form dp minus z dq. Minus p, dz minus p dq, sorry, dz minus p dq. And what I'm saying is that if I know the slope dq dz, I just let that be my p coordinate. So I have that, I'm just projecting away the p coordinate, and that's the Legendrian. And there's a unique way to sort of build this such that the tangent space is killed by this one form. Okay. So that's kind of a degree down what I can do. I started just with the data of S1 together with 3 points, and I was able to build this Legendrian. Instead, I could try to play the same game where I start with S2, which I'll think about as R2 union infinity. But my starting combinatorial data will be, say, G, which I'm going to have be a trivalent plane graph. Right, I was trying to go across. So maybe let me write this here just for. So S2G is a trivalent plane graph. By which I mean that it looks something, say, like this.
Kevin,
yes.
would you mind writing a little bit bigger for us here online?
Yeah, I can write bigger. Yes, sure.
Thank you.
That's good. Yeah, let me know if there's anything else that's hard to see from online as well. I'm happy to oblige. Okay. So I have this graph that I've drawn, has a bunch of vertices and a bunch of edges. Each vertex has 3 outgoing edges. That's what it means to be trivalent. And when I say plane, I mean that this graph is explicitly embedded in S2 up to some isotopy of embeddings. And so you can ask, is there sort of, what's the analogous picture that I have? And the analogous picture is the following thing. So I have 3 kinds of points on S2. There's points, say, like this one right here, where what I do is I think about in S2 cross R now. So in S2 cross R, if I had one of these yellow points where nothing was happening, I just have that I basically put 2 disks and I separate them in the R direction. So I have these 2 disks like this, which lie over this disk here. So I separate them in the R direction. If I have a point at an edge right here, well, I have some sort of edge which is running over here, and I want some kind of double cover. So what I do is I just have that this edge is going to represent some kind of crossing. So I have kind of 2 things, kind of 2 sheets that are crossing each other on this edge. And finally, if I have, say, a point that's at a vertex here, and this is harder to draw, what I do is I'm imagining that I have something which, well, on the edges, it has to look like these 2 are crossing each other. And I have that over where it's not over an edge, it has to just be a double cover. And then something's happening at this point. So what I have is a double branched cover of a disk. And I can imagine that the boundary of the disk kind of goes up and then down and then up and then down and then up like this. So it's kind of this is the graph. Am I too far to the right? Okay. This is the graph of the real part of, say, z to the 3/2. In a second.
So it's not like every well, maybe you'll.
Yeah. If you like, what these are doing, these are building 2-strand braids, just a dimension down. And these are building sort of, so these are kind of some sort of immersed branch double covers in S2 cross R. And now you can take its Legendrian lift in the one jet space of S2. So you can take the Legendrian lift, lambda g, inside of the one jet space of S2, which is T star S2 cross R, where you think that the projection down to S2 cross R is just this immersed surface that I drew. And it's immersed, but because the slopes of these near this edge are different, you get that it ends up becoming an embedded Legendrian in here. So this construction, so these are called, nowadays they're called Legendrian 2 weaves. I'm supposed to write bigger. Legendrian 2 weaves. Although that terminology came sort of later, these were originally studied by Treumann and Zaslow. So it's a certain family of Legendrian surfaces which are embedded in the one jet space of S2. Okay. So what's nice about this family is that, first of all, it's represented by combinatorial data. It's represented by trivalent plane graphs. That's quite a lot of things that you could draw. And not only that, but what was I going to say? Not only that, but they're quite, they're things that you can get your hands on quite a lot. So already in the work of Treumann and Zaslow, they had understood what sheaves should look like for these things. So I mentioned this representations are sheaves, and already the moduli space of sheaves was essentially understood in that paper of Treumann and Zaslow. So let me say what that is. Oh, I'm not supposed to be so far to the left.
Oh, you're good.
Okay. So what should the sheaves be? Well, the sheaves should be constructible sheaves that live on S2 cross R. And they should look something like the following thing. So if I imagine I have a trivalent plane graph, let's just suppose that I have a face of this trivalent plane graph here. And I have that here's kind of my S2. And I have an R direction, which is going up. Then the sheaves that should correspond here, what they should be is they should be locally constant, except when they pass through the front projection, so this immersed surface in S2 cross R. In particular, what they should look like is the following thing. If we're studying rank R representations in particular, they should be 0 down here. They should be something like F to the 2R up here. But now, if I think about what's going on over this face, I had these kind of 2 sheets, one going up here, one coming down here. And every time I pass through this from the bottom up, I should have that the cone, there should be sort of a cone map from whatever this is here to whatever it is here. These are representing the stalks of some sheaf, some locally constant thing, except for where it passes through these strata. And what that means is that inside of here, I have an F to the R with maps from this 0 to this F to the R. So I have a 2R dimensional vector space, and inside of each face, I have a rank R vector space. And it should satisfy some conditions. So it should be that if I look at a neighboring face, so this FR, then the corresponding subspaces of this F2R that I get should be transverse to each other. So combinatorially, the data that I care about in my sheaves, essentially what it is for each of these faces, what I'm going to do is I'm going to put on it an element of the Grassmannian R planes. So each of these comes with a label of a Grassmannian R plane in 2R dimensional space over F, such that any neighbors are transverse. If you like, that's some interesting quasi-projective variety, where in the case of R equals 1, if I think about what's happening for R equals 1, just as an example, then what I'm doing is I'm looking at face colorings by elements of the projective line FP1, where by face colorings, I mean that any two faces that are next to each other should be distinct. You hear me now? Can you, how about now? Yeah? Okay, good. Okay. So the story really starts with this work of Nadler, Zaslow, and Nadler, which says that there's a quasi-equivalence between the infinitesimally wrapped Fukaya category on the cotangent bundle with some moduli space of constructible sheaves on M. And in particular, if I have that if I have some kind of Legendrian, at least in the boundary of T star of M, so if I can imagine that, so if I have some Legendrian inside of the unit cotangent bundle, then I can imagine what I can do is I can take some kind of Fukaya subcategory where I consider Lagrangians that are kind of asymptotic to this Legendrian, and I should have that there's a corresponding subcategory of sheaves. So I should have some kind of subcategory on both sides with respect to these, which should correspond. Yeah.
So then it's like the representation thing, like the graph category of small disk.
Right. It's exactly. So yeah. So yes. I mean. So right. At the very least, at a sort of more naive level, just to sort of say, this is kind of representing some kind of Floer theoretic information, and encoded here are things like Legendrian contact dg-algebras. And so that should correspond to something here on this side. And the thing it should correspond to in this case are these moduli space of sheaves of the correct microlocal rank if you're looking at representations of rank R. Okay. Yes.
So the augmentations are one-dimensional.
Yes. Yes.
Okay, so then on the sheaf side, what is the dimension of the representation? Correspond to the dimension? Is it rank something or?
Yeah. So on the sheaf side, yeah. So on the sheaf side, I put an R here. I put an R here everywhere, and it's just replacing this with an R. So what the microlocal rank essentially means is that I'm thinking about this as a locally constant sheaf. And so when I pass through a stratum, I can imagine here that I'm passing through, say, some stratum. And I can imagine that if I take a point on the stratum, so there's a sheaf, so I have sections of this sheaf. And so in particular, there's restriction maps to here and to here. And that allows me to say that, what is this 0 representing? It's basically saying, well, this 0 kind of gets mapped through here to here via the restriction maps. Like one of them's an isomorphism, depending on your conventions. I forget exactly which one's the isomorphism. But so that's what this map is actually saying. And being microlocal rank R essentially means that the cone of that map is rank R. Is really occurring in some derived category, and it just turns out that when you take the moduli space, you should, lots of things are equivalent to each other, so you can mod out to the correct place. So on the other side, Legendrian, well, maybe let me just say, so in terms of representations are sheaves, a little bit about what's been done. So quite a bit has been done in the case R equals 1. So R equals 1, which are called augmentations. So for knots, this has been verified. This is due to work of Ing, Rutherford, Shende, Sivek, and Zaslow. And in fact, what they prove actually for knots is that they end up getting an A infinity categorical equivalence. not just a bijection. Also, in terms of augmentations, there's the case of conormal tori. So these are Legendrian surfaces due to Gao, Honghao Gao. Proved this for conormal tori. He also looked at links, taking conormal Legendrians of links. And there's something a little bit weird that happens there where there's not an exact correspondence between augmentations or sheaves. But it's a little bit technical. And for general Legendrian surfaces with mild singularities, we have that Rutherford and Sullivan proved that there's a map from augmentations to sheaves. So they don't show any sort of equivalence of these things, but they do construct a map of this sort. Oh, yeah, okay, that's fine. And for R greater than 1, there's not so much work that's been done, but at the very least, Chantrain, Ng, and Sivek verified that representations are sheaves for for 2n torus nets. Okay, so the goal of the second half of the talk now is to basically say, well, we don't have so many examples of representations, but I'm claiming that for the Legendrian surfaces, which I just defined, that we can still compute these things quite explicitly. And we can verify representations, so we can bring representations to a much larger family of examples. And in particular, the first time that's been done for Legendrian surfaces and not just Legendrian knots. Okay, any questions about the goal setup? Okay. So how do we think about representations? Oh, I should also mention one more paper. It would be bad if I didn't. Let me make sure I get all the authors right. Just in terms of this, in terms of representations, one of the tricky things is how to deal with non-commutativity. A lot of times when people compute Legendrian contact dg-algebras, they do it in terms of coefficients which could be commutative, like in homology groups. And obviously for higher rank representations, we're looking at things where we're mapping to matrices which might not commute. So you actually need to compute things with coefficients that don't commute. And in terms of handling that in the correct algebraic way and what sort of the proper statement is for representations or sheaves, I should mention this paper of Chantrain, Dimitroglu, Rizal, Eugenie, and Golovko. Okay. Okay. So they define all sorts of statements about basically how to handle the algebra that you should have in terms of what representation should mean for these sort of Legendrian contact type thing. Yeah, for the DG algebra, exactly. It has non-commutative in the title. Non-commutative. I don't remember the exact title, but if you look up these authors with non-commutative, you'll find it. Yeah. Okay. So back to our case. So G is a trivalent plane graph. Well, the first thing that we need to do is we need to compute the Legendrian contact dg-A. So LCC star, say, of this guy with its differential, by which I mean, so this is the Legendrian contact dg-algebra. Or the Chekhanov-Eliashberg dg-algebra, as it's sometimes known. Okay. And so Casals and Murphy computed it. With respect to, with coefficients in the first homology of the Legendrian. So they had a paper, cubic planar graphs and differential graded algebras, something like that. And they actually computed this, and although it's not written there in terms of the Legendrian contact dg-algebra, if you read the introduction, you'll see that it is essentially a computation. And essentially, in order to do this, what they had done was they worked out the gradient flow trees in order to compute this. So using technology of Tobias Sackel. A remark is actually that this, as I've said it, this Legendrian contact dg-algebra, it's interesting, but it's not actually so interesting, as we'll see in a second. But their version is very combinatorially enhanced. There's all sorts of things that you can do. And really what they're doing is they're really doing this for the satellite of this Legendrian instead. So you can imagine that instead of just taking the Legendrian, living in the one-jet space, you can instead embed it into R5 in a sort of standard way, where if the Legendrian lives inside of the one-jet space, and I also have that S2 is living inside of here, if I take the unknot, U, inside of R5, then the one-jet space, I can basically identify the one-jet space. Let me say it this way. So I take an open neighborhood of the unknot here, and I take U inside of here. I can basically identify a neighborhood of the unknot with the one-jet space of S2 and use that to embed this Legendrian into R5. So this is called the Legendrian satellite. And the dg-algebra becomes much more interesting just because even sort of a dimension down, if I look at if I look at kind of this guy that I drew here, well, this case isn't so interesting because I haven't drawn enough crossings. But if I look at this guy that I've drawn here and I take the satellite, essentially, I'm going to draw exactly the same guy, but where I kind of have to close it off in some sort of way. So, okay, I've drawn a Legendrian unknot, but imagine that I drew 5 crossings instead and wasn't as lazy. And you see that there's now going to be all sorts of, there may be Rabe chords between the top 2 strands and the bottom 2 strands. Whereas here, the only Rabe chords that I get are sort of 1, 2, and 3 Rabe chords. There's now a whole bunch of extra Rabe chords that I get. In fact, I can do this in such a way that I basically get 4 extra Rabe chords if I'm careful. So really what I should do is I should take this 1, 2, 3. I should take this, and then I kind of go up really high, and then I kind of come across like this, And essentially, those 4 extra Rabe chords are the 4 guys that kind of go from one of these top 2 things to one of these bottom 2 things. So I can imagine that if I'm looking at gradient trajectories now, these gradient trajectories are allowed to travel across to the right, and they can break sort of here. So they do the same thing, but a dimension up, which is, you know, an interesting combinatorial thing to do. And so last year, I generalized their computation to work, instead of just over H1, I can now work with pi1 of the Legendrian relative to some base point where I actually have to specify the base point in some kind of way. So it's essentially the, you know, the same kind of computation. And really, I did the combinatorially interesting case of the satellite. But it doesn't really matter if you're only interested in representations, because all of these generators basically have degree 2. So it's kind of irrelevant if you're only caring about representations. But I did this computation, plus I included all sorts of functoriality. So in order to compute this, you can imagine that you had to make a bunch of choices. You had to choose some scheme of perturbations in order to compute these gradient flow trees. And how you make those choices actually will affect the result, including, for example, when you take the satellite, you might change the face at infinity where you take the Legendrian satellite. So I cover all of the functoriality that can happen. So what I mean is this. I mean that, so Casals and Murphy, they prove that the Legendrian contact dg-algebra that you get for the satellite is independent of a whole bunch of auxiliary choices that you can make, which they put into something called a garden. And so, okay, they show independence in that way, but you might then ask, for example, there's a bunch of those choices where if you want to go from one choice to the other, you can imagine that as being realized by a Legendrian isotopy. And then you can ask, what if I have a contractible loop, for example, of Legendrian isotopies? So I actually show that it's not just an isomorphism, but actually that the corresponding loop is isotopic to the identity, is chain homotopic to the identity itself. So I sort of go one step further. I don't go to homotopies of isotopies, but I do show at the very least that these contractible Legendrian loops give you chain homotopies. Chain homotopic to the identity. Okay. So how do I compute this pi1? Well, what I do is the following. So I imagine that I had my graph as before, whatever it was. There it is. And what I do is I choose the tree. So pick a tree, T, spanning all but one vertex. So I'm going to choose, maybe this is my special vertex up here. I choose a tree. So this might be hard to see, especially for the folks at home, but hopefully it's clear. I've chosen a tree. And what I do is for each face here, what I have is I have a canonical path to this point, which I'm going to take as my base point, which doesn't cross the tree. So if you like, these are sort of capping paths for all points that don't hit the tree. In particular, well, I'll say in a second. So I do this for everything, including the face at infinity. And now I need to tell you what happens when I go through one of these edges. So when I go through one of these edges, if I have an edge, come on. There's essentially I have two possible paths I can take. I can either go, say, from plus to minus, or I can go from, let's say I go from plus to minus regardless, but I can choose to go from the plus face, the one that's sort of out more, to the minus face in either direction. In homology, those are inverses. So if you want to recover the Casals-Murphy computation, you just take these to be inverses to each other. But in this case, these are not actually inverse to each other. So what you do is for every edge that's in your tree, you take these two generators. Maybe I'll call this lambda and lambda bar. Maybe I'll call it lambda e and lambda e bar. Okay. Well, there's also a relation between these things. So if I take a little loop around any vertex, and I go around twice, so I can imagine going from plus to minus to plus to minus to plus to minus, that traces out some word in these generators. And I can think all I'm doing is, when I go from plus to minus, I can imagine I'm starting here and sort of making everything based at the base point by sort of following along this path. And then I go from plus to minus, I come back, go along, come back, go along, come back. So I do this everywhere. And so at every vertex, I get some word, say WV. And that's our model for the fundamental group. It's just that. Is that what I wanted to do? No, I wanted here. I just have that pi1 is equal to, sort of I take this collection of lambda e's and lambda e bars, where I'm doing this over all trees, and I now take these words, WV, for all vertices. So this is great because it gives me just a way, sort of a combinatorial space where if I have some gradient flow tree where I want to write down what my differential is, so I want to write down the corresponding element of pi1 in my gradient flow, the only thing I need to do is essentially record it as some kind of word where I remember that I've sort of modded out by some other word. Okay. So maybe that's a little lemma. And so now I have to tell you sort of, how do I compute the Legendrian contact dg-algebra of this? So now if I look at this picture and I just think about where the Rabe chords are, remember that each of these faces is like an inflated pillow of some sort. And the Rabe flow is coming out of the board. So I can imagine that there's kind of a maximum place, like where the pillow is highest, where the pillow is most inflated. So actually what each of these central points are, those are the Rabe chords. I have one Rabe chord for each face. And now you wonder, what are the trajectories which emanate from that face? What are the trajectories that emanate from that face? Well, because this is a maximum, if I start following gradient trajectories of the difference between the heights of these two, if I start following gradient trajectories of that difference function, I'm going to have that I basically have paths which emanate outwards in all directions. And some of those paths, you see, some of those paths are going to come to this edge. But those are no good. You cannot have a gradient flow tree which goes to an edge. That's not a possible place for a gradient flow to emanate. So the only possibility that you have is that you have some flows which go to these vertices. So in fact, you have these kinds of flows that are going to these vertices. And if you've seen gradient flows before, you're a little bit worried because you say to yourself, well, I need that my flows kind of, they can end at Rabe chords or they can end at cusp edges. And I don't see either of those here. But that's OK. These are degenerate types of singularities. You can basically deform it to make it non-degenerate. And then you can, and then it turns out that there's a single trajectory which will come from here to here. And so each of these counts basically once. And what is the corresponding element of pi1 that's going to give me? Well, if I think about what that curve really is, there's sort of two sheets that are coming down to this point. And I have that I'm looking at some kind of gradient trajectory, which is sort of flowing from a Rabe chord. So here's a Rabe chord into what actually is a cusp after making this non-degenerate. And so the curve that I'm getting is something which kind of, it comes here and it goes back. It's basically a perturbation of something that goes once around here. Yeah.
That's like a dumb question. Probably just ask one time.
Yeah, sure.
Okay, so I'm really having trouble with the picture here. So we're computing like the Legendrian dg of just a single Legendrian cubic surface.
Just that.
So not like the dg of like a two copy or something like that. Or...
No, so it's the Legendrian surface and its front projection is immersed. So I have these two sheets are both part of that immersion.
Yeah.
And then
we're also allowing ourselves to these class type singularities.
So what I'm saying is that when you want to count gradient flow trees, you need to make things degenerate. This type of singularity, this sort of graph of the real part of z to the 3/2 is not degenerate. However, it doesn't really like if you make it degenerate, you can see that there's one curve that's going to basically end. Once you know that, if you think about just this neighborhood of this vertex, which remember is a branched double cover of a disk, if I look at what's happening as I come in, so sort of everything up to here, when it enters that neighborhood, it enters the plus part and it comes back out of the minus part. And it does something inside this disk. Well, what's happening? This is just a disk, which is sort of branched, it's kind of branched like this. And it's coming in from the plus side and it's going out to the minus side. So there's actually only one homotopy class of curve from here to here. So even like the fact that there's just one trajectory, if you want to know what its class is in pi1 of the surface itself, you know sort of what's happening up to here. And then because there's only one of them, and I know this is unique here, that gives me a unique homotopy class. And you see, I wiggle this so that it no longer touches the vertex, and it just basically goes around the vertex here once.
I don't really know this flow tree formalism very much. I mean, I guess I can just ask about it.
Yeah, maybe I should have said a little bit more, but so yeah, so let me maybe say that for a second. So essentially the idea of flow trees is the following thing. If you study what's happening with holomorphic curves which emanate from a Rabe chord, then what you do is you sort of take a limit, an adiabatic limit, where you sort of squish your Legendrian. Then what happens is the holomorphic curves are becoming more and more and more vertical. So they start to look like more and more vertical things. And the direction that so if I had a Rabe chord, say, between two sheets like this, then the direction that they will sort of, the holomorphic curves will travel in is if this is the graph of a function f1, and this is the graph of a function f2, then essentially the direction that they're going to travel in is going to be given looking from above at minus the gradient of f1 minus f2.
Okay, so basically, I mean, is the thing that I should be thinking of like these sort of like types of Legendrians you're considering are sort of like graphs of like branch functions or something like that?
Exactly,
so
exactly.
Okay, so then you're just kind of using the, like if it was just a graph of something, then you could really just use the
exactly.
The holomorphic curves between the zero section and the original thing using gradient.
Exactly.
Sure.
You have to be a little bit worried about, in this case, there's only two sheets. In general, certain things can happen if there's more sheets, which is why the satellite case is sort of more interesting.
Yeah.
Because if there's sort of three sheets where you imagine I have kind of a sheet like this, I have a sheet that's coming down like this, and I have a sheet that's going up like this. I can imagine something that kind of, it's coming in here, and then all of a sudden it kind of splits off into this direction and this direction, like some kind of curve like that. So from above, that will look like, here it sort of comes in and then it splits, where here it's like, ij, and maybe here it's like ik, and here it's kj or something like that.
Okay.
So, and there's other things that can happen as well. But in this case, there's not so much room for things to happen. When you do the satellite, there are more interesting things, but.
Sure. Okay. That's good enough, I think.
Thank you. Other questions? Okay. So in the end, the dg-algebra that we build is essentially just the following thing. We work with coefficients which are in this pi1, which we just computed. And then what we do is we make those coefficients also non-commute with the free non-commutative associative algebra over the Rabe chords, which remember, we're just in bijection with the faces. And the corresponding Rabe chords that we have here, so these are in degree 1, whereas these elements here, these are all degree 0 elements. The coefficient ring is degree 0. And we just saw how to compute the differentials of the faces. We saw that the differential of the face, so if I have this face here, right there, I just look at a sum of each of these guys. Where the corresponding element that I associate to one of those is the following thing. So I can imagine here's the face. Say this is EI, EJ, and say EJ and EK. And I have something coming in over here. Well, I just said that the homotopy class of that, you could imagine sort of following it around in this kind of way. So that's going to be something like del F is going to be a sum over all of the vertices of things which look like, say, lambda EI, maybe let me just call it lambda I, lambda K bar, lambda J, something like that. We have to be a little bit careful about what your orientations are, but essentially it's just what we said we should encode this homotopy group as. Once you cross, you put an element there. And so what are representations? If this is my dg-algebra, so if I call this algebra, say, A, I'm looking at maps from A, so graded, so degree 0, maps from A to just say GLRF with the property that if I look at what happens with the differentials of the faces, these have to go to 0, because those are the only things that are in degree 0, which are, at least that generates the ideal in degree 0, which represents the image of the differential. Oh, sorry. Right. Right. R by R matrices, where remember that because I have that this is an algebra map, if it's an element of pi1, it gets mapped to something invertible. Thank you. Yeah. So all of these elements, lambda I, lambda K bar, lambda J, those are all getting mapped to some sort of invertible elements. And so you can just think that this representation, you can alternatively think about it as some kind of, it's living in the character variety, which is really maps from pi1 of lambda G, del star, to GLRF. So there's some sort of correspondence between representations and maps to here, which essentially satisfy the property that when I sum the matrices corresponding to these things, I get 0. Okay. It's the sum over all vertices, yeah. I'll just write. That's the whole differential. Yep. F goes to 0 because this is degree 0. And sorry, I forgot to say one thing. If you want to work over Z, you should put signs plus or minus. Yeah. How much time do I have? Probably 2 minutes. OK. So let me just say a little bit about, just a word about how you actually get this map from pi1. How you go from this map from pi1 to GLR to actually get one of your sheaves. What you do is you say the following thing. So let's fix a base point once and for all on this graph. Say my base point is here. So I'm going to draw all of these kinds of, let me draw them in a different color. So I have all of these sort of gradient trajectories that I said occur in this dg-algebra. And there's also the ones at infinity. I won't draw all of them. And what I'm going to do is I'm going to fix a base point, say, in here. And now for any non-degenerate curve that I have, so by non-degenerate, I mean it's not going to pass through any of sort of the triple points or anything like that. So for any curve here, say to here, what I'm going to do is I'm going to start, and in this triangle, so now I have a triangle which is sort of separate, I've kind of cut along also these gradient trajectories. I'm going to put here just the matrix, the 2R by 2R matrix, which is I0, 0I. And I imagine that as I pass through this, one of two things happens. I either pass through one of these kinds of trajectories, and suppose that the trajectory is going this way. Then what I do is I'm going to associate to this a matrix, which is of the form I, and then the corresponding plus or minus lambda I, lambda k bar, lambda j, 0I. Whoop. And if I pass through an edge, then when I pass through this, I associate it to it the matrix, which is of the form 0, the corresponding lambda for that edge, lambda bar inverse 0. And because if I've chosen a representation, this is now just an invertible R by R matrix, and each of these is an invertible R by R matrix. So that allows me now to take this element and just for everything here, I now get this triangle gets identified with some element of GL2R of F. It turns out that that's actually a well-defined element if you have a representation, because if I go around this whole thing, I'm just multiplying elements of this form. And it turns out that around any vertex, I always get that it's coherent. So automatically, I get that I can specify these elements GL2RF. And if I just take the first R rows and take the spans of them, so I take the span of the first R columns. That ends up giving me an element in the Grassmannian that I was interested in. When you look at moduli spaces, that turns out to be a bijection. OK, that's it. Thank you very much. Yeah.
So that differential doesn't have any chord components? Like it's just the differential. I mean, I guess it has chords that are coming from this layer.
Yeah, so these, the only rabe chords that you have are just at these faces, yeah. Again, unless you do the satellites. If I had more time, I would have talked about sort of why this is maybe the right thing to do, how you see it in the satellite. But But anyways, yeah, the only wavecoords that you get when you don't satellite are just at these. So the entire dg-algebra is just spanned in this way. And so the only thing you need to take a differential of are the wavecoords. And of course, you extend by the Leibniz rule to get the differential on everything. But because the representations only care about the degree 0 part, you just need to know what happens to these degree 1 generators anyway for the representations. Yeah. Yeah, so it looks something like that. So the way that I like to think about these matrices is in the following way. Okay? Imagine that I had an extra sheet above this, and imagine that the slope of the extra sheet was such that its gradient, like I imagine that this is all happening near something of slope 0. And so I look at the difference between this slope of 0 and sort of something out here, which is kind of coming along. And I look at what's happening as I travel along this. When I look at the gradient trajectories, now we have to consider those more interesting types of things. Those can now happen. And in particular, you can imagine that when I pass one of these red guys, so the red guys are called threads. And you can imagine that I have like, here's this thing that's way up there, and there's sort of like this kind of doubled piece down here, which is approximately flat. So I'm traveling along here. I have that my gradient trajectory, maybe it's from up here, and it's traveling along, and it's on the bottom piece. But then all of a sudden, it hits one of these red guys. And that red guy, see what it could do, what this red guy could do, is you could either include it or not. There's two possibilities. You can either now come along here, and now you're sort of considering continuing in that direction. Or you could have where you're also, you also have, so because this is approximately slope 0, this is still going to go about the same way. Or you could have just passed through it and not cared about it. So you could have done the same exact thing where you kind of passed through here, you didn't care about it. And so now you just have this guy. And then there's also one more possibility, which is just you were actually between the top two anyway, in which case nothing could have happened here. So those basically correspond to the following things. If you think about each contribution, that you have when you're computing sort of the Legendrian contact dg-algebra with this hot thing that's all the way up here, you have that those three contributions. Well, you could have done nothing, or you could have changed the corresponding element of pi1 that you're counting by including this extra element. So that corresponds, you can't switch from one way to the other, but you can switch from the opposite way. So in that sense, what I think is that the bordered theory, what it's essentially saying is you're supposed to build some kind of bordered theory over this, whereby you're imagining that any path that you take, you can basically let it be sort of, this kind of thing, this extra piece here, and then compute the Legendrian contact dg-algebra, how the Legendrian contact dg-algebra sort of changes along that path. So if I were trying to build a bordered theory, which basically did this, this is the kind of picture that I would like to have in mind. This is why the satellite case is interesting, because actually there's two strands here, and they're sort of realizing exactly.